Hey guys, this is Professor Janacek, and I'd like to talk a little bit more about limits. This time we're going to look at L'Hopital's rule. Suppose that we take the limit as x approaches a of f of x over g of x, and the result is 0 over 0. Or we take this limit and the result is infinity over infinity, and those infinities can be either positive or negative. Notice in this case, x can approach a real number or it can approach positive or negative infinity. If that's what we end up with, and notice by the way that these results are what we call indeterminate forms. So if we take these limits and we get one of those indeterminate forms, it turns out that according to L'Hopital, we are allowed to take this limit and rewrite it as the limit as x approaches a of f prime of x over g prime of x. It's very, very powerful and very, very handy. Again, we do have to start with one of those indeterminate forms of either 0 over 0 or infinity over infinity. And then when we rewrite this limit, again, these limits are equal, but notice we take the derivative of the numerator and the derivative of the denominator. We are not using the quotient rule here. Let's take a look at some examples so we can see how this works. If we were to take the limit as x approaches 0 of sine of x over x, simply evaluating this limit using substitution, we get the sine of 0 over 0, which of course is 0 over 0. Now, 0 over 0 is one of those indeterminate forms, but it's one that works well with L'Hopital. So we can't do that, but we can instead invoke L'Hopital's rule, where we take the derivative, we're still using the limit, but we take the derivative of the numerator and the derivative of the denominator. So we end up with the limit as x approaches 0 of simply cosine of x, which we can evaluate that using substitution and simply get 1. Wasn't that nice? Example 2 here, we're taking the limit as x approaches infinity of e to the x over x squared. If we were to simply evaluate this limit as x goes to infinity, e to the x also goes to the infinity, and x squared goes to infinity, which is not going to work for us. However, it is ready to go for L'Hopital's rule. So we begin by taking the limit of the derivative of both the numerator and the denominator. So the derivative of e to the x in the numerator is still e to the x. The derivative of x squared in the denominator is 2x. But if we try to evaluate this one again in the numerator as x goes to infinity, e to the x goes to infinity, and in the denominator as x goes to infinity, 2x goes to infinity as well. So we end up with infinity over infinity, but let's invoke L'Hopital's rule one more time. We're still taking the limit. In the numerator, we take the derivative of e to the x, which is still e to the x. And in the denominator, we take the derivative of 2x, which is simply 2. Now, if we evaluate this limit as x goes to infinity, e to the x goes to infinity as well, divide that by 2, and we still get infinity. All right, not so bad. Again, this only works for those indeterminate forms of 0 over 0 and infinity over infinity. And again, those infinities could be positive or negative. What if we have some of the other indeterminate forms, such as 0 times infinity, or infinity minus infinity, 1 to the infinity, or 0 to the 0, or infinity to the 0? Any of these forms, what we'll have to do is we'll want to rewrite it in one of the original forms so that we can apply L'Hopital's rule. So let's take a look at a couple of those. First off, example 3, we have the limit as x approaches 0 from the right of x times the natural log of x. Well, of course, as x goes to 0, what we get here is 0 times the natural log of 0 The natural log of 0, though, is as x approaches 0 from the right, that takes us to negative infinity. So we're ending up with 0 times negative infinity. Not going to work, and it's not even one of our original forms. So we have to do something with this. What can we do? Well, let's begin by rewriting that function. Instead of x times the natural log of x, I'm going to write this as the natural log of x divided by 1 over x. Yeah, look at that. Rather than multiplying by x, I'm dividing by 1 over x. Yes, we know that if we divide, it's the same as multiplying by the reciprocal, but it turns out that if you're multiplying, it's the same as dividing by the reciprocal as well. Okay, now notice what we have. As x goes to 0, the natural log of x goes to infinity, and 1 over x also goes to infinity. So here we have infinity over infinity. We are ready to use L'Hopital's rule. Notice I still have to write this limit notation. Don't forget about that. The derivative of the natural log of x in the numerator is 1 over x. The derivative of 1 over x in the denominator, be careful with this, we actually end up with negative 1 over x squared. So now if we simplify this limit, or this function, we have 1 over x times negative x squared over 1. This simplifies. We are taking the limit of negative x. Again, I'm just reducing those x's. And as x goes to 0, negative x also goes to 0. And there we go. Let's take a look at one more. Now in this case, if you look at what we've got, as x goes to infinity, we end up with infinity raised to the, notice that exponent is 1 over x. As x goes to infinity, 1 over x goes to 0. Again, that's not going to work for us, and it's not even one of my original indeterminate forms. Again, don't forget, it must be 0 over 0 or infinity over infinity. So we don't have that. Let's see if we can get it. So we'll start with the limit as is. Now here's a fun little trick. I say trick, technique. What I'm going to use is inverse functions. I know if I put inverse functions together, they kind of cancel one another out. They undo one another in operations. So I'm going to use the inverse functions e and the natural log. So make sure you understand what just happened there. I'm using both e and the natural log together, and putting them together in this form actually results in just the exponent. Now, you might have in algebra or pre-calculus used this going the other direction, but here in calculus, we can build up and use this to our advantage. Now, the beauty of this is that I can now use the property of the logarithm up there in the exponent and get 1 over x times the natural log of x in the exponent. So now we have e raised to the natural log of x over x. Now, what happens as x goes to infinity here? The natural log of x also goes to infinity, so we get e to the infinity over infinity, and that is one of the forms I can work with. I'm happy with that form, but of course I'm not allowed to really do this. So let's get rid of that and try again. Using L'Hopital's rule, I have the limit. Actually, let me rewrite this just to make sure that everything's proper. Remember, properties of limits allow me to rewrite this with the limit just there in the exponent. Okay, now I'm going to use L'Hopital's rule. keep that limit up there in the exponent, but take the derivative of the numerator and the denominator. So we end up with, in that exponent, just the limit of 1 over x. And as x gets really large, 1 over x gets really small. So we end up with e raised to the 0 power. And of course, we know that that is 1. And there we go. Enjoy!